Slide 1 Introduction. Greetings, students. Today, we delve into an intriguing problem from LeetCode titled Minimum Window Substring. This challenge invites us to explore the fascinating world of string manipulation and algorithmic design. The crux of the problem is to identify the smallest contiguous substring within a given string that encompasses all the characters from a specified set. We are presented with two inputs, a primary string and a secondary string containing the characters we must include. Our objective is to find the shortest segment in the first string that contains each character from the second string at least once. Should such a substring not exist, we simply return an empty string. For instance, consider the input string Adobe Code Bank and the target string ABC. The substring bank emerges as the shortest segment that includes all characters A, B, and C, thereby fulfilling the problem's requirements. Let us embark on this intellectual journey to unravel the depths of this algorithmic challenge. A frequency array with a hash map is a powerful data structure that helps us count how often elements appear in a collection, like an array or a list. Think of it as a way to create a simple inventory system for our data. Each unique element acts as a key, and its count is the value associated with that key in the hash map. This setup allows us to retrieve and manipulate counts efficiently. For example, when we want to know how many times a certain item appears, we can just look it up in constant time, making our operations much faster compared to searching through the entire collection. To use this method, we start with an empty hash map. As we go through each element in our collection, we check if it's already in the hash map. If it is, we increase its count. If not, we add it with a count of 1. This straightforward process not only summarizes our data quickly, but also lays the groundwork for solving many algorithmic problems, especially in data analysis and statistics. In this example, we'll explore how to create a frequency array using a hash map, which is a powerful way to count occurrences of elements. First, we initialize an empty dictionary called frequency map. This dictionary will act like a storage box where each key is an element from our list, and its value is the count of how many times that element appears. As we loop through each element in our input list, we check if it's already in our dictionary. If it is, we simply increase its count by 1. If the element isn't in the dictionary yet, we add it with a count of 1. This process allows us to efficiently tally up counts. Finally, we convert our dictionary into a list of tuples, making it easy to read. For example, when we pass in a list with several fruits, the output shows how many times each fruit appears, like 3 apples and 2 bananas. This method is not only efficient, but also clear and easy to understand, making it a great tool for problems like the minimum window substring. The sliding window technique is a powerful method used to tackle problems involving sequences, such as arrays or strings. Imagine you're looking through a rectangular window that can slide along a wall. This window represents a subset of your data. You have 2 pointers, one at the start and one at the end of the window. As you slide this window across your data, you can examine different parts without having to repeatedly check everything. This technique significantly improves efficiency, reducing time complexity from quadratic to linear. For example, when trying to find a substring that meets a specific requirement, you can expand the window by moving the end pointer to include more elements. Once a condition is satisfied, you move the start pointer forward to narrow the window. In essence, the sliding window technique allows you to dynamically assess data in a way that saves time and resources, making it a versatile and essential tool in algorithm design. The sliding window technique is a powerful approach for problems involving sequences, like our example here. Minimum window substring. In this function, sliding window sum, we're calculating the sum of every contiguous subarray of size k in the given array. First, we compute the sum of the initial window, which consists of the first k elements. This sum is stored in window sum and also added to our results list. Next, we slide the window across the array. For each position, we adjust the window sum by subtracting the element that's leaving the window and adding the new element that's entering. This way, we avoid recalculating the entire sum from scratch, which saves time. Finally, we return our results, giving us the sums of all sliding windows. This method is efficient, enabling us to process the array in linear time, making it ideal for large datasets. The two pointers approach is a powerful algorithmic technique often used to tackle problems involving sequences, like arrays or linked lists. Imagine you have two people walking along a path. One starts at the beginning, while the other starts at the end. They move towards each other, adjusting their speed based on specific conditions they encounter. This is similar to how the two pointers technique works. By using two pointers, we can significantly reduce the time it takes to find a solution. Instead of checking every possible pair of elements, which can lead to a time complexity of O(n) squared, we can achieve linear time complexity, O(n). This efficiency is especially useful for problems like pair searches or managing overlapping intervals. In practice, one pointer might search for a specific element, while the second helps track the range of values we're interested in. This coordinated movement allows us to explore the data effectively, minimizing unnecessary checks and computations. By understanding and applying this technique, you can optimize your solutions and improve performance in many algorithmic challenges. In this example, we're using the two-pointer technique to solve a problem involving an array. We start by initializing two pointers, left and right. The left pointer begins at the start of the array, while the right pointer starts at the end. Next, we prepare an empty list called result to store our findings. The key here is that we loop until the two pointers meet. During each iteration, we check if the element at the left pointer is even. If it is, we add it to our result list. Then, we perform a similar check for the right pointer. After checking both ends, we move the left pointer one step to the right and the right pointer one step to the left. This way, we systematically examine the array from both ends, collecting even numbers along the way. Finally, we return the result list, which now holds all the even numbers we found. This technique is efficient and helps us process the array in a single pass. To solve the minimum window substring problem, we employ the sliding window technique along with hash maps for efficient character counting. First, we initialize two dictionaries, need, which tracks how many times each character appears in the target string t, and have, which monitors the character counts in our current substring window of s. We also set two pointers, left and right, both starting at 0, and initialize a variable valid to count how many unique characters from t are currently satisfied in the window. We also keep track of min length to find the smallest window. Next, we populate the need dictionary by iterating through t to create a frequency map. As we slide the right pointer across s, we update the have dictionary and check if the current character meets the requirement in need. When all characters are satisfied, we then try to contract the window from the left, updating our minimum window length if we find a smaller valid window. We repeat this process until we've explored S. Finally, if we found a valid window, we return the substring. Otherwise, we return an empty string. This approach runs in O(n) time, making it efficient and effective for our needs. Today, we explore LeetCode problem 76, which asks us to find the minimum window substring within a string S that contains all characters from another string T, including duplicates. This task is particularly challenging given that both strings can reach lengths of up to 100,000 characters, requiring an efficient approach. Furthermore, we must consider that S and T consist solely of English letters, digits, and symbols, adding complexity to our substring search. Let's delve into the solution. The provided Python solution tackles the challenge of finding the minimum window substring in string S that contains all characters from string T. It utilizes a sliding window technique, which is an efficient way to manage the substring boundaries. The algorithm starts by using a default dict to count how many times each character appears in T. This allows us to quickly check character frequencies in constant time. We also define two important variables: required, which counts the unique characters we need from T, and formed, which tracks how many of these characters we currently have in our window. To represent our current substring, we use two pointers, L and R, to define the left and right edges of the window. As we move the right pointer R to expand the window, we update a window counts dictionary with the characters we encounter. When the number of characters we have in the window, represented by formed, matches required, we know we have a valid window. At this point, the algorithm attempts to minimize that window by moving the left pointer L to the right, checking if the new window is smaller than the previously recorded minimum. By maintaining this structure, the algorithm efficiently finds the smallest valid window with a time complexity of O(n plus m), where n and m are the lengths of strings s and t. This approach not only showcases the power of data structures like hash maps, but also demonstrates effective algorithm design principles in action. Time complexity for the minimum window substring problem is O(n plus m). Here, n represents the length of string s, and m represents the length of string t. This is because we first need to traverse both strings to create frequency counts of the characters. Think of it like shopping. You make a list of things you need, which is akin to creating the frequency counts from string t. Then, as you go through your shopping, you check off items from your list, similar to scanning through string s to find the minimum window that contains all characters from string t. Now, regarding space complexity, it's OM. We use a hash map to store the frequency of characters in string t. This hash map's size will be determined by the number of unique characters in t, which can be at most m. Imagine your shopping list again. If you have a list of m different items, that's the maximum space you'll need to remember them. This efficient use of space is crucial for optimizing our solution. Understanding these complexities helps appreciate the algorithm's efficiency in solving the problem.